Okay guys, let's take a look at today's lesson. So today what we're going to be doing is we're going to be working with systems of conics. Really a two-part procedure. What we want to do is we want to graph them, and the graphing is for just a couple of different reasons. We're really not graphing to find the actual solutions, because many times the solutions aren't exact, aren't integers. You know, they're like weird fractions or radicals. So the really two reasons for graphing is, one, it gives us an idea of how many solutions we should have, right? That tells us, looking at the graph, we should know how many solutions we have, unless our graph is just so off that we can't tell. But you guys are really good at graphing, so I'm not worried about that. The other is just to practice graphing, just to practice more graphing. That's really the reason that we graph. We're actually, once we graph, it gives us an idea of what we're up against, and that's when we solve the equation. Now these are conics, so they have like x squareds and y squareds and a bunch of different things in them, and they can get a bit challenging. So let's work through a couple and then we'll go from there. So let's start with the first one. And the first one, we look at that and we see that it looks like we've got an ellipse here, and that would be a parabola. Just looking at those, we can kind of tell what those are going to be. So let's get this in the proper form to graph. So we'll divide everything by 36, and that would give us x squared over 36 plus y squared over 4 equals 1. Okay, so let's graph that ellipse. So the center is at 0, 0, and our a is going to be 6. 1, 2, 3, 4, 5, 6 on either side. And then b is 2. Okay, so since we're just graphing for solutions to a system, there's no reason to, graph the focus points or the, any of the other parts of the ellipse. We just need the outside of it. We just need the outside. So that's what we're looking at, something like that. The next one, that is a parabola, so let's get this in a proper form so we can graph it. So let's see, we would have x squared is 2y plus 4. I need to work on it so I can see what a is going to be. So I would factor out a 2. Now, some students get a little confused here, and they just kind of leave the 2 there. This does not represent a, right? A only occurs by the x squared and y squared variables. It doesn't occur over here with the single y and single x variables. So I've got to move that over to actually know what a is. So I'd have y plus 2 equals 1/2 x squared. Okay, so this is just all our work on graphing. So what this tells me is my x coordinate of my vertex is 0 and my y coordinate is a -2. Right, that's what that tells me. So let's just get a different color. So my x coordinate is, let's see, 0 and -2. Now, if you want to, you can get a more accurate graph, maybe find the, the zeros or something. You don't have to. I'm not going to require you to draw a perfect graph. It just needs to be fairly representative of the figure. So it actually does go through 2 and -2. But again, we don't need to be perfectly accurate, just a good sketch. So looking at that sketch, it should indicate how many solutions we're looking for, and it looks like we should have 3. It looks like we should have 3. So there are really 2 different types of solving techniques to use on these. One is elimination and one is substitution. I'm actually going to talk about both of them with this first one. I'm going to talk about elimination first. So if I were to do elimination here, and I were to subtract the second one from the first one, you see how my x squareds would go away? That would be actually pretty convenient for me. I would only be left with y's. This would be a pretty good one to do elimination with, right? Because it really eliminates the x's, and I'm just left with a bunch of different y's. So let's see, 9y squared minus nothing is 9y squared. 0 minus a -2y is a plus 2y. And 36 minus 4 is 32. So that's kind of nice. It kind of put me right where I want it to be, which I would factor that. Now I'm actually going to do this one by substitution. I'm going to show you it doesn't really matter which way you do it. You're going to come out with the same answer. So let's kind of hold there. Let's do substitution as well. Because I want you to see that we are so accustomed to solving for a single x or a single y that sometimes we don't think about other things that we could solve for. Right, so we might just want to solve for y here, and then we'd have a bit of a mess, wouldn't we? We'd have a fraction like a half x squared. I mean, we'd have a little bit of a mess. Could you do that? Yes, you certainly could. But instead, why don't we solve for x squared? Because I have an x squared here, and I have an x squared there. So I could substitute in for x squared. So it's another kind of thing to think about. So I'm going to take this second equation and solve it for x squared. So I have x squared equals 2y plus 4. And then what I'm going to do is I'm going to take this portion right here, this 2y plus 4, and I'm going to substitute it in the other equation for x squared. I'm going to replace x squared with the 2y plus 4. So I have 2y plus 4 plus 9y squared equals 36. So that is with substitution. And you can see as I'm going to move that around, I'm going to end up with the exact same quadratic that I did to end up with by doing elimination. So I move the 36 over, I get 9y squared plus 2y, and that's going to give me a negative 32 equals 0. So these are the same. Either way, you can get to the same exact quadratic. So now we're going to factor, and this factors to be 9y minus 16 and y plus 2. So my y values are 16 ninths and negative 2. Now, from time to time, I have some students that just kind of like to leave a jumble of x and y values and are like, oh, here's the answer. That's not really the answer. We want to know the actual coordinate points where these intersect, not just a little random listing of x's and y's. So we got to pair them together. We're looking at two different y values to find the x values, and we've been doing this for years, right? We know we substitute back into one of the equations to get the other, we want x. So I actually subbed in here just because the numbers were smaller. I could have subbed anywhere. I just subbed into the second one. I thought it would be easier. So that's x squared minus 2y equals 4. So x squared minus 2 times 16 ninths equals 4. So x squared equals, I'm going to move that over, that's 32 ninths plus, and what, 36 ninths. So x squared is, what is that, 68 ninths. Or x is a plus or minus, and the square root of 68 simplifies to 2 root 17. 2 root 17 over 3. Those are my x coordinates that go with that y of 16 ninths. So I'm going to pair those up. So I have 2 root 17 over 3, 16 ninths, and negative 2 root 17 over 3, 16 ninths. So far, those are two of my solutions. Now I'm just going to kind of reference the graph as I go. As I look at these solutions in the graph, it appears that what I've found are these two up here. Right? That's what that looks like. So we're good to go. We have one more solution to find. So that comes from the y equals negative 2. And I would like to use the same equation. So I have x squared minus 2 times negative 2 equals 4. Or x squared equals, what that's before, subtract that over 0. So x is 0. So let's see if this makes sense. Do we have a solution at 0, negative 2? And that does make sense. That's this solution right here. So that gives us our solutions. How are we on that first one? Okay? Okay, let's look at the next one. The next one, we have a hyperbola, which is already set to go, set to graph. So let's do our little, it's one space on either side. Our vertices are on the x-axis. And then looking at our asymptotes, we would draw those through. Okay, it looks like our hyperbola would look something like this. Okay, and again, no need to draw, you know, focus points or anything like that. We just really need the curve. We need to look at the curve and see how it intersects the other curve. So the second equation, that looks like that's going to be a parabola. So if I move the x squared over, let's just kind of get it ready in a little bit of a better form. So I move the x squared over, and then I have negative 1 equals negative 1 minus y. Let's factor the negative 1 out. So I have 1 plus y equals negative x squared. So this is the little equation we want to work with. This is just for graphing purposes. So our vertex would be, let's see, would be an x coordinate of 0 and a y coordinate of negative 1. Let's go ahead and just do a different color. So here, and then it's a negative x squared, so it's going to open down, you know, something like this. And it really does not appear, it doesn't appear that those cross. It doesn't look like we should get a solution. So we just need to be aware of that. Maybe when we solve this, we may not, you know, may not have a solution. Let's see. What I did is I solved this one for x squared, and I subbed in for x squared. That's how I did it. Of course, there's lots of different ways to do it. I encourage you to do whichever way you like, but I took the second one and solved for x squared, and then subbed it into the first one. So x squared is going to be y plus 1. Okay, and then I'm going to take that and put that, oh no, I did this one, sorry. I took this first one and I moved, just so I could keep things positive, I moved the y squared over, and I have x squared equals y squared plus 1. So I'm taking the top one and I'm solving for x squared and subbing it into the bottom one. So y equals negative 1 minus, and then I'm going to open this spot for x squared and insert the y squared plus 1. But again, you could have done it the other way too. It doesn't really matter. Whatever you like. So let's just kind of clean that up, distribute. So I have negative 1 minus y squared minus 1. I'm going to move everything to the left in preparation for hopefully factoring. So I have y squared plus y plus 2. Now we've been factoring for a pretty long time, right? We look at that, we're like, that's not going to happen, which means we pull out old trusty quadratic formula, right? Our trusty little friend. Oh, quadratic formula. So negative b plus or minus square root of b squared minus 4 times a times c all over 2 times a, and whoa. Yeah, we don't even have to go any farther. You don't need to find the imaginary roots. There's no sense. We want real roots. So we look at this, we're like, yeah, that's going to be imaginary. These are imaginary. So what does that mean for our purpose? We're trying to solve, right? That means we have no solution. So we did, you know, we did draw the graph pretty well. We did draw it. You know, there's always a, well, is my graph very accurate? It is pretty good. They do not intersect. Now I just want to talk about another kind, because there's another kind on your daily work that some students were having a really quite a bit of a problem with. So what I'd like to do is talk about it and just kind of set up the structure on how you would do it. So perhaps you haven't seen this way to do it before. Maybe that's the trouble that we were having earlier. So let me just erase this, and I'm just going to write one of the problems up. If it's going to let me erase it. Oh, that's just lovely. There we go. Okay. So let's look at a situation like this one, where we have a circle, and we have another circle, so what I want to do is I want to take you through the thought process on how you would do something like this. Now, and there's another one on here where the circle is actually has, it's in proper form where the square has been completed. if the square's been completed, you just still need to multiply it all out. Okay. So what do we do with something like that? That's kind of a mess. Could we solve for either x or y? Yeah, but think about what that would entail. Then I'd have a plus minus radical. It'd be really weird, kind of a mess. So another option that I would encourage you to try would be elimination. So let's just choose elimination right here. And what's going to happen to my x squared and y squared variables? They're going to be gone. And then I'm going to have, so those are gone. So I have 0. I still need to keep the equals lined up. I have 0 minus a minus 12 is 12. 0 minus 6 is a negative 6. And then 5 minus a negative 25 is what, 30? Check my arithmetic because I'm doing this on, okay. So very strange that we have something like that. We're left with a line, and what I encourage you to do is to solve for x or y. Seems more convenient to solve for y. Why? Then I avoid fractions. I don't want to hurt fractions' feelings, okay? I know that fractions are a lot of fun, but really working with them is not easy. So I like to avoid it. So I would solve this for 6, for 6y. So I'm going to move this over here. So 12x minus 30, and then divide everything by 6. Again, check my arithmetic. Is that we good? Okay. Now it's like, well, how did that help? We still have an x and y. Well, the way it helped is that now I'm going to take this expression, this 2x minus 5, and I'm going to substitute it for y in one of these equations over here. So now I am down to one variable. That's a big deal, right? That's very helpful. So that's the technique that I encourage you to try, and I wanted to point it out. I'm not going to finish it for you, but that's what you would do, is you would get it down to a line, and you're going to take this and go back to either one you want. Doesn't really matter. Y equals that. So I probably would go back here, and I would say 2x minus 5 equals negative 1 minus x squared, and then go from there. Now I'm down to one kind of variable instead of having both x's and y's, and my life will be easier. Okay, so those kinds of problems are a bit more complex. They require multiple steps, and students kind of derailed on that earlier, so I wanted to point that out to you. Are we okay with that? Okay.